Hello friends, welcome to my channel. Let's have a look at problem 2373, largest local values in a matrix. So in this video, we're going to practice the sliding window method, and also we're going to practice using the sliding window with the transpose of the given matrix. And at the same time, we want to use set abstract data structure due to the problem nature. So first, let's look at the statement of the problem. So we are given an n by n integer matrix called grid. So we would like to generate an integer matrix called max local of size n-2 by n-2 such that so the local ij is equal to the largest value of the 3 by 3 matrix in grid centered around row I plus 1 and columns j plus 1. So in other words, we want to find the largest value in every contiguous 3 by 3 matrix in grid. So we are required to return the generated matrix. So here are two examples. So I'm going to look at example 1 only. So here the number of rows or number of columns of the square grid is 4. And because we are considering 3 by 3 grid, so the output should be 4 minus 3 plus 1, that is 2 by 2. So if we look at the top left corner, none elements, so the maximal is none, so this is none. And similarly, we look at the top right, none numbers, so we're going to have another none. So if we look at the lower bottom left corner, none elements, so the largest one is 8, so we have 8 here. And if we look at the bottom right corner, none elements, so we will get the maximal is 6, so we get a 6 here. So this is example 1. So now let's look at the constraints. So here first it specifies that the grid is a square matrix. In other words, the number of rows and number of columns are the same. So the second element, the second constraint, actually the first one is that n is no less than 3. So in other words, so this is the valid problem. Secondly, n is bounded above by 100. And also the last assumption or constraint specifies the range of elements in the grid, that is between 1 and 100. So with that said, let's look at the method we're going to present. So this problem actually is sliding window. So here we're going to use both the original grid or original matrix, or we can use the transpose of the matrix. And because this problem is compute the max, so we're going to use a set data structure in between. So here actually we want to make a remark, that is, for a n by n matrix, if we compute local matrix using m by m filter or patch, so the result is another square matrix of n minus m plus 1 times n minus m plus 1. So here the plus 1 is to be noticed. So in this problem, so m equals 3, right? So now we want to give an interpretation of this problem. So if you know something about neural network, for example, convolution neural network, so we can actually interpret this as a convolution of kernel size m by m. So here m equals 3. So with max as aggregate function or downsampling function. So this is actually exactly the problem. So here is example 1. So if we use the original grid, so if we look at this 3, so we're going to get the 1 element, none, right? So if we look at this 3, 5, 6, 2, and 8, 2, 6, and 6, 2, 2, we are going to get this elements, right? So if we're using the transpose, so actually, so this one, 958, 962, 826 is going to give us this one. And then if we look at the this one, say 962 and 826 and 164 is going to give this one, right? So this problem actually is marked as easy by Leetcode, as it is. But the thing is that this problem is not trivial, so we need to pay attention to the indexing when we write the code. So here the plan is the following. First, I'm going to practice sliding window using the original matrix. And then for fun, we're going to do the sliding window using the transpose. So both of the two methods, we're going to use set abstract data structure. So before we write the code, here is a remark. So can we further simplify the code we are going to share? So here, actually, the code we are going to write is for the purpose of demonstrate the understanding, not pursuing the shortest code. So let's first look at the WAM format solution. So we're going to sliding window using original grid, right? So for this, so I want to try to demonstrate the general case. So I'm going to let n equals the length of the grid. So because it's a square matrix, so this n is number of rows or number of columns. So I'm going to introduce a variable to make it a general code for general m. So here m equals 3, right? So we do not need to, it's not necessary to introduce this variable, but here we prefer to do this way, meaning that we don't only want to solve this specific problem. So now the result actually is a matrix, so with size n minus m plus 1, right? So we're going to use a dummy index for range, so n minus m plus 1, right? So if m equals 3, so actually this expression is n minus 2, right? So let's regard this one as step 1, preparation. So with that said, we are ready to do the sliding window, right? So here, because we are computing a max, right? So I'm going to use a set, because if an element appears many times, so it does not affect the nature of the max, right? So for this, I'm going to do the iteration. So for I in range, so n minus m plus 1. For j in range, n minus m plus 1. So this n minus m plus 1 times n minus m plus 1 is the size of the result. So we're going to assign each element for this result. And then for this, I'm going to initialize a reference set. So initially, it's an empty set. Then we're going to add the corresponding blocks to the reference set and then get the maximum. So for this, I'm going to, because I want to write in a generic form, so actually I'm going to write another loop. So this loop actually is just 3. So for L, so let's see, for L in range m, then I'm going to add, so ref union with set the corresponding elements grid, so I plus L, and then so this is corresponding to extract the corresponding rows. For example, if we consider S elements, so we need to consider I plus 1, I plus 2 rows, and the corresponding J, so it's J from J to J plus M, right? So that's actually very generic. So we generalize, just not for m, not only for m equals 3, but for generic m. So with that said, I guess, so after we get the reference set, so this is all the unique numbers corresponding to the block or convolution kernel at consideration. Then we are going to reset the result ij to be the max of the reference, right? So for example, if there are a lot of same elements, so this reference set maybe just have one element. For example, this corner is just have a 1. So with that said, I guess we are ready to do the return. So we just need to return the final state of this 2D array result. So with that said, we are ready to write the to test the code. Yeah, it passes example 1. Now let's do a generic case check. Yeah, it passes all the cases. So as our plan specified, so this is the first version of the code. So let me copy this function signature and then mark this as v1, and then we write another one. So here I'm going to do sliding window using the transpose of grid. So essentially it's the same solution, but we want to practice a function called zip, right? So zip can be used to transpose a matrix. So first I'm going to get the preparation. Let's see, get the length of grid same as above, and so for this I want to write it more specific. So let's transpose. So transpose to be, so here I'm going to use a list and zip. I want to pass the star grid. So this zip function, so we corresponding to put this one as to a tuple to this zip function. So this actually returns a iterator. Then if we make it a list, so this corresponding to a representation of the transpose of the matrix grid. So then, so this, for example, in example 1, it corresponding to this matrix. So next we are going to do the iteration. So again, so we are going to get this result by say. So here I'm going to write m equals 3 just for specific, for more specific. So next we are going to do the iteration again. So sliding window using transpose and set ADT. So for this we're going to iterate like I in range. So n minus 3 plus 1 up to for G in the same thing, n minus 3 plus 1. And then what we want to do is that we initialize a reference set, let's call it empty set, and then we want to find the corresponding blocks. For example, if we want to set one element here, so we need to look at this and this and this, right? So if we look at 586, 622, and 262, we're looking at here, right? So if we slice to this 3, then we're going to look at first 3, so we're going to look at this corner, right? So then let's add the corresponding things. So this time I'm not writing in such a format for loop. I'm using a more specific format. So ref union with set. So basically the transpose. So we're going to use J here and I to I plus 3, right? So then I'm copy this one twice. So I'm going to change this to be J plus 1 and here J plus 2. So this actually plays a similar role. And then I'm going to after this for loop, after this after adding all the 3 vectors, or after adding the sub patch, so we're going to reset the result ij to be max of the reference, right? So now we're going to do the return. So we're going to return the final state of the result. So let's do a special case check for this case. Yeah, it passes example 1. Now let's look at the generic case. It passes the generic case. So here, one thing maybe we can do is that we can print the corresponding set. For example, if we look at example 1 here, let's check. So yeah, for example, this numbers, actually there are 5 unique numbers. So the largest one is 9. And then for the second case, so it's 9, 8, 6. So with that said, actually we finished another version of the solution. So for sure, this code can be further simplified. but I will stop here for this problem and this video. Thank you very much for your time. That's it.